In the 1950s, physicists discovered a particle that broke the rules. It appeared in cosmic ray showers, born in violent collisions high in the atmosphere, created easily and abundantly. But then it refused to disappear. It lingered for what seemed like an eternity by subatomic standards, billions of times longer than it should have survived. Nothing in the known laws of physics could explain why. They called it strange, and they meant it literally. That one word would become the name of an entirely new property of matter. But the strangeness didn't stop there. This particle would go on to shatter one of the deepest assumptions in all of physics, the belief that nature's laws treat matter and antimatter as perfect mirror images. What physicists found inside this particle didn't just add a new entry to the catalogue of subatomic objects, it forced them to rebuild the foundations of particle physics from the ground up. If you find this kind of deep dive into the hidden structure of reality interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference. Now, let's begin. In 1947, the subatomic world seemed almost manageable. Physicists knew about a handful of particles. There was the proton, the positively charged particle sitting inside the nucleus of every atom. The neutron, its electrically neutral partner, is bound alongside it in that same nucleus. The electron, the tiny negatively charged particle orbiting far outside. The photon, the particle of light. The positron, the electron's antimatter twin, was discovered back in 1932. And there was the recently confirmed pion, the particle that Hideki Yukawa had predicted in 1935 as the carrier of the strong nuclear force between protons and neutrons. That was essentially it. You could list every known fundamental particle on a single index card. The universe appeared to be built from a small, tidy set of building blocks, and physicists had good reason to believe the list was nearly complete. That comfortable simplicity was about to be shattered. High on mountaintops around the world, physicists were studying cosmic rays, high-energy particles that constantly stream in from deep space, slamming into atoms in Earth's upper atmosphere at tremendous speeds. When one of these fast-moving particles strikes a nucleus, it produces a cascading shower of secondary particles that rain down toward the surface, like debris flying out from a collision. In the late 1940s, cosmic rays were the only source of particles energetic enough to probe the deep structure of matter. There were no powerful accelerators yet, no machines capable of smashing particles together at high enough speeds to create new forms of matter. If you wanted to study what happened in nature's most violent collisions, you had to let the universe do the colliding for you. Cosmic rays were the universe's own particle accelerator, and that meant going to the mountains, where the atmosphere was thin enough that the secondary particles from cosmic ray collisions hadn't been absorbed before reaching your detector. Physicists hauled their equipment to high-altitude observatories and research stations. Mountaintop laboratories perched in the Alps, the Pyrenees, the Andes, anywhere the air was sparse and the cosmic ray flux was strong. The primary tool of choice was the cloud chamber. A cloud chamber is a sealed container filled with supersaturated vapor, usually alcohol or water vapor, cooled to just below the point where it would condense on its own. The vapor is on a knife edge. It's ready to form droplets at the slightest disturbance. And when a charged particle passes through this vapor, it ionizes molecules along its path, stripping electrons from atoms and leaving a trail of electrically charged ions behind. Those ions act as seeds for condensation. Tiny droplets form along the trail of ions, creating a visible line of white mist tracing the particle's journey through the chamber. The result is a thin, delicate track, like a miniature jet contrail frozen in midair, recording the path of something far too small to see directly. By placing the chamber inside a magnetic field, physicists could bend these tracks. A positively charged particle curves in one direction. A negatively charged particle curves the opposite way. The amount of curvature tells you the particle's momentum. Heavier, faster particles leave nearly straight tracks. Lighter, slower particles curve sharply. Combined with measurements of track density and length, you could work out the particle's mass, charge, and energy. Cloud chamber photographs were the fingerprints of the subatomic world. You couldn't see the particles themselves, they were far too small for any optical instrument, but you could read their tracks and reconstruct what had happened, like a detective studying footprints left in fresh snow. Every photograph was a crime scene frozen in time, and the physicist's job was to figure out what particles had been involved, where they came from, and what they turned into. It was painstaking, meticulous work. You might run your cloud chamber for weeks at a high-altitude station, shivering in the cold, taking thousands upon thousands of photographs. You'd develop the film and scrutinize each frame under magnification, looking for unusual tracks, unexpected curves, or mysterious patterns amid the clutter of ordinary particle trails. Most of the events were mundane, familiar particles doing familiar things, electrons spiraling, protons scattering, and pions appearing and decaying exactly as expected. But occasionally, very rarely, something would appear that didn't fit. A track that was too heavy to be an electron, but too light to be a proton. A pattern of decay products that didn't match any known particle. An event that made you stop and stare and pull out your calculations to check whether what you were seeing was even possible. In 1947, at the University of Manchester, two physicists named George Rochester and Clifford Butler found exactly that kind of event. In their cloud chamber photographs, they spotted tracks shaped distinctly as the letter V. Two particle trails emerged from a single point, spreading outward at an angle, diverging from each other like the arms of the letter. This was the unmistakable signature of a neutral particle decaying into two charged particles. The original particle itself left no track because it carried no electric charge. It had been born somewhere upstream in the cosmic ray cascade, had travelled a measurable distance through the chamber, and had then spontaneously split apart into two charged particles, whose diverging trails the chamber faithfully recorded. The V-shape was a smoking gun. Something unseen had been there, something unstable, something that no theory had predicted and no physicist had expected. Rochester and Butler published their results, and at first, the reaction from the wider physics community was cautious. A few peculiar tracks in a cloud chamber were intriguing, certainly, but not necessarily conclusive. Maybe the photographs had been misinterpreted. Maybe some unusual combination of known particles had mimicked the appearance of a new one. Extraordinary claims require extraordinary evidence, and a handful of V-shaped tracks did not yet meet that standard. But within the next few years, as more research groups around the world joined the search, the evidence became impossible to dismiss. Physicists working at high-altitude stations in the French Pyrenees, at observatories in the Swiss Alps, and at facilities on mountains across multiple continents began finding more of these unusual particles. And not just V particles. They found a growing menagerie of entirely new objects. Some were heavier than protons and decayed into protons and pions. These would eventually be identified as lambda and sigma baryons, heavy particles carrying this mysterious new property. Others were lighter, clearly mesons, decaying into pions and other combinations. Some were electrically charged, leaving their own visible trails before splitting apart. Others were neutral, betraying their presence only through the V-shaped tracks of their decay products. By the early 1950s, the trickle of discoveries had become a torrent. Cloud chambers and photographic emulsions at high-altitude stations were revealing dozens of events that couldn't be explained by any known particle. And every single one of these new particles shared the same deeply puzzling characteristic. They were produced quickly and abundantly in high-energy collisions, but they took an absurdly long time to decay. This might not sound like a crisis, but in particle physics, it was one of the most confounding puzzles anyone had ever encountered. To understand why, you need to know something important about the forces that operate at the subatomic level, and specifically about how fast each force works. The strong nuclear force is the most powerful force in nature. It is the force responsible for binding protons and neutrons together inside the atomic nucleus. Protons are positively charged, and positively charged objects repel each other through the electromagnetic force. Inside a nucleus, protons are packed absurdly close together, squeezed into a space less than a trillionth of a meter across. The electromagnetic repulsion between them at this distance is enormous, and yet the nucleus holds together. The strong force overwhelms that repulsion and binds the protons and neutrons into a stable structure. That's how powerful it is. The strong force dominates everything at nuclear distances, and it is incredibly fast. Interactions governed by the strong force happen on a timescale of roughly 10 to the minus 23 seconds. This number is so small that it resists comprehension. Light, traveling at 300,000 kilometers per second, the fastest speed in the universe, can barely cross the diameter of a single proton in that time. That's how fast the strong force operates. It acts on the timescale of light crossing a nucleus. In the world of subatomic particles, the strong force is essentially instantaneous. The weak nuclear force is a completely different animal. It is responsible for certain kinds of radioactive decay, processes like beta decay, where a neutron transforms into a proton, emitting an electron and a neutrino. The weak force is far slower than the strong force. Processes governed by the weak force typically happen on timescales of about 10 to the minus 10 seconds. Now, 10 to the minus 10 seconds might still sound unimaginably fast to a human being, and it is. But compare it to the strong force. 10 to the minus 10 is 10 trillion times slower than 10 to the minus 23. Those 13 orders of magnitude between the two timescales represent an enormous gulf. If the strong force timescale were 1 second, the weak force timescale would be roughly 300,000 years. The two forces operate in completely different temporal universes. In the subatomic world, where everything happens at speeds that make a lightning bolt look frozen, the weak force is like geological erosion. It gets the job done eventually, but it takes what feels like forever. Now here is the paradox that consumed the physics community. When these new particles were created in cosmic ray collisions, they appeared rapidly and in large numbers. Cosmic ray protons would crash into nuclei at tremendous energy, and the new particles would fly out of the wreckage copiously and without hesitation. The speed and abundance of their production bore the unmistakable fingerprint of the strong force at work. The strong force was clearly making them. And this is where the logic breaks. If the strong force knows how to create a particle, the strong force should also know how to destroy it. Creation and destruction are simply the same interaction running forward and backward. They are time-reversed versions of each other. A particle born through the strong force should decay through the strong force, which means it should disappear in about 10 to the minus 23 seconds, so quickly it would barely travel any measurable distance before disintegrating. But these particles did not do that. They traveled visible distances through cloud chambers. They left tracks long enough to photograph and measure, tracks spanning centimeters. They lived for roughly 10 to the minus 10 seconds, about 10 trillion times longer than the strong force should have allowed. They were being created by the strong force, but dying through the weak force. And nobody could explain why the strong force, which clearly had no trouble assembling these particles, seemed completely unable to take them apart. Imagine you are watching a builder construct a house in a single afternoon. He works incredibly fast, assembling walls, fitting windows, raising the roof, all in a matter of hours. The house goes up almost instantly, but then, when it comes time to demolish the house, the same builder puts down his tools and walks away. Instead, a single person with a small hammer begins tapping at the walls, one brick at a time, slowly and methodically taking the structure apart over the course of years. The builder who put it up could have knocked it down just as fast. Nothing was stopping him. He had the strength and the tools. But for some mysterious reason, he was forbidden from touching the house once it was complete, and the demolition had to proceed through a far slower process. That is essentially what physicists were watching at the subatomic level. The strong force built these particles instantly, but then it seemed locked out, unable to reverse its own work. The particles had to wait for the weak force to slowly dismantle them. Something invisible was preventing the strong force from destroying what it had created. The first major breakthrough came from paying close attention to how these particles were produced. Physicists, combing through thousands of cloud chamber and emulsion photographs, noticed a striking and consistent pattern. These strange particles were never created alone. Every single time a cosmic ray collision produced one of these new particles, another one appeared alongside it, always in pairs. You never saw a single strange particle produced by itself in a strong interaction. Two appeared together, or none appeared at all. The pattern held across hundreds of observed events, in experiments conducted by different groups in different countries using different detectors. It was not a coincidence, it was a rule. In 1952, a Dutch-American physicist named Abraham Pease proposed an explanation that was both simple and profound. He called it associated production. The idea was this: suppose these new particles carry some previously unknown quantum number, a new internal property of matter that nobody had yet identified. And suppose the strong force is required to conserve this property, meaning the total value must remain the same before and after any strong interaction. If one particle in the pair carries a positive value of this new property, and its partner carries a negative value, then creating them together keeps the total at zero. The books balance. Conservation is satisfied. The strong force can produce the pair without violating any rule. But here is the crucial part. Once the two particles are created and fly apart, each particle is on its own. And a single particle, sitting alone, cannot decay through the strong force without changing the total value of this new property. The strong force is forbidden from doing that. Conservation laws are absolute for the strong force, so the particle is stuck. It carries this property and cannot get rid of it through the strong force. It has to wait for a different force, one that does not obey this particular conservation law. It has to wait for the weak force. And the weak force is 10 trillion times slower. That single fact explains the entire paradox. Creation is fast because pairs conserve the hidden property. Decay is slow because individual particles must rely on the only force willing to violate it. This was an audacious proposal. It demanded the existence of an entirely new property of matter, something fundamental that had been invisible until cosmic rays reached high enough energies to expose it. But the logic was airtight, and the experimental evidence supported it beautifully. Strange particles really were produced in pairs, always, without exception. Something was being conserved when they were made, and violated when they decayed. The full mathematical theory arrived in 1953 and 1954, when two young physicists working independently on opposite sides of the world arrived at essentially the same complete framework. Murray Gell-Mann, working at the University of Chicago, and Kazuo Nishijima, working in Japan, each developed a rigorous scheme that assigned specific values of a new quantum number to every known particle. Gell-Mann gave this quantum number a name that perfectly captured the confusion it had caused. He called it strangeness. It was not meant to be whimsical. These particles genuinely were strange. Their behavior defied every existing expectation, and the property that explained that behavior deserved a name that conveyed the bafflement of an entire generation of physicists. In the Gell-Mann-Nishijima scheme, the rules were clear and surprisingly elegant. Ordinary particles, protons, neutrons, pions, all had a strangeness value of 0. The new particles had strangeness values of +1 or -1, and some of the heavier, newly discovered baryons had strangeness values of -2 or even -3. The strong force and the electromagnetic force both conserve strangeness. Any process mediated by either of these forces must leave the total strangeness unchanged. The weak force, however, is permitted to violate strangeness conservation, but only by 1 unit at a time. This simple rule, strangeness conserved in strong and electromagnetic interactions and changed by 1 unit in weak interactions, explained everything. It explained why strange particles were always produced in pairs. It explained why they decayed slowly. It explained the specific decay chains that experiments observed. One elegant principle resolved a paradox that had consumed the field for years. Among all the strange particles being discovered, the kaon quickly emerged as the most important. Kaons were mesons, a class of subatomic particle with masses falling between the lighter leptons, like electrons, and the heavier baryons, like protons and neutrons. The word meson comes from the Greek word for middle. The most familiar meson before the kaon was the pion, confirmed in 1947, which Yukawa had predicted as the carrier of the nuclear force between protons and neutrons. Pions had been expected. Pions made sense. They had strangeness 0, and they behaved exactly as theory said they should. They were the well-behaved children of the particle world. Kaons were entirely different. They were the lightest mesons that carried strangeness, which made them the simplest and most accessible examples of strange matter. The positively charged kaon had a mass of about 494 million electron volts, roughly half the mass of a proton, and about 3.5 times heavier than a charged pion. The neutral kaon was slightly different in mass, sitting at about 498 million electron volts. Both carried 1 unit of strangeness, making them the lightest, cleanest laboratories for studying this entirely new property of matter. And because they were the lightest strange particles, kaons were also the easiest to produce. When the first generation of powerful particle accelerators came online in the early 1950s, machines like the Cosmotron at Brookhaven National Laboratory in New York and the Bevatron at the Lawrence Berkeley National Laboratory in California, kaons became the workhorses of experimental particle physics. For the first time, physicists could produce strange particles on demand in controlled laboratory conditions in huge numbers. They no longer had to haul equipment up mountainsides and hope the cosmic rays delivered something interesting. They could aim beams of protons at fixed targets and generate showers of particles, including kaons, reliably and repeatedly. They could measure production rates, decay times, branching ratios, and angular distributions with a precision that cosmic ray experiments could never dream of. The age of accelerator physics had begun, and the kaon was at its center. Nearly every major advance in the understanding of strangeness came from studying kaons. The associated production hypothesis was confirmed by meticulously tracking kaon production in accelerator collisions and verifying that strange particles always appeared in pairs with opposite strangeness. The quantum number assignments proposed by Gell-Mann and Nishijima were tested by measuring how kaons decayed and comparing the observed patterns against theoretical predictions. Everything matched. The framework held. Strangeness was not a guess or a convenient fiction. It was a genuine, measurable, conserved property of nature, as real and as fundamental as electric charge. And the kaon was the particle that proved it beyond any reasonable doubt. But the kaon's importance went far deeper than just confirming a new quantum number. It forced physicists to confront a question they had not previously taken seriously. If strangeness had been lurking in nature all along, completely invisible until particle energies were high enough to produce strange matter, what else might be hiding? How many undiscovered properties of matter might there be? Before strangeness, a particle was fully defined by its mass, its electric charge, and its quantum mechanical spin. Those three numbers told you what the particle was and how it would interact. Strangeness revealed a fourth property, one that had been entirely invisible under normal conditions and only manifested at extreme energies. This raised an unsettling possibility. The properties physicists knew about might be only a fraction of the properties that actually exist. Nature might be carrying quantum numbers that nobody had any reason to suspect, waiting to be uncovered by the next generation of experiments. That possibility turned out to be correct, and the consequences were staggering. Over the following decade, as accelerators grew more powerful and collision energies climbed higher, the number of known subatomic particles exploded. By the late 1950s and early 1960s, physicists had catalogued not dozens, but hundreds of new particles, each with its own mass, charge, spin, and strangeness value. Heavier mesons, excited baryons, resonances that lasted for barely 10 to the minus 23 seconds before disintegrating. The sheer number became overwhelming. Physicists began calling the situation the particle zoo, and the name reflected genuine frustration. It felt like chaos. Every time someone built a bigger, more energetic accelerator, more particles came tumbling out. The Nobel laureate Willis Lamb reportedly joked that the Nobel Prize in Physics should be awarded to any physicist who did not discover a new particle that year. The universe that had seemed so clean and simple in 1947, built from a few elegant building blocks, had become bewilderingly complex. The confusion was not merely a matter of bookkeeping, it was a genuine intellectual crisis. Physicists had grown accustomed to the idea that fundamental particles should be few in number, and that the laws governing them should be elegant and economical. The periodic table of chemical elements had seemed complicated at first, with over 60 elements known by the late 1800s, until Mendeleev showed they followed a repeating pattern that revealed deeper structure. Physicists expected the same thing to happen with particles. The zoo should organize itself, a pattern should emerge. But for years, no pattern did. Theorists tried numerous approaches, and most of them failed. Some attempted to classify particles by mass alone, sorting them into families based on how heavy they were. But particles of similar mass often had wildly different charges, spins, and strangeness values. There was no consistent scheme. Others tried to use symmetry groups from pure mathematics, applying abstract algebraic structures to the particle catalogue in hopes that some group would organize the data. Most of these attempts were too simple or too contrived. They would explain some particles but leave others orphaned, dangling outside the pattern. And whenever a new particle was discovered, which happened with disturbing regularity, the proposed scheme would usually break. There was also a deeper worry, one that gnawed at the foundations of the entire enterprise. If protons and neutrons and pions and kaons and hundreds of other particles were all truly fundamental, all irreducible and structureless, then the universe was built from an absurdly large number of basic ingredients. That offended the physical intuition of nearly every working physicist. Nature had always rewarded the search for simplicity. Atoms explained the diversity of chemical compounds. Protons, neutrons, and electrons explained the diversity of atoms. At every previous level, apparent complexity had turned out to be the result of a small number of building blocks combining in different ways. The particle zoo screamed that the same principle should apply one level deeper. Hundreds of particles should not be fundamental. They should be built from something smaller, something simpler, something that combined in different configurations to produce the observed variety. But what? Nobody knew. The building blocks, if they existed, had never been seen directly. and for nearly a decade, from the mid-1950s to the early 1960s, the puzzle remained stubbornly unsolved. And yet the Kaon had already planted the seed of the answer. Strangeness was not just a fix for one particular paradox. It was a fundamental organizing property. The particles in the zoo were not a random collection. They fell into families, grouped by their strangeness and other quantum numbers, arranged in geometric patterns that hinted at a deeper level of structure underneath. The key to unlocking the zoo was to take strangeness seriously, to treat it as a property just as fundamental as electric charge, and to search for the mathematical symmetries connecting different particle families to each other. That search would eventually lead to the quark model and to a complete revolution in how physicists understood the architecture of matter itself. But before that revolution could happen, the Kaon had more to reveal. What matters here is this. The Kaon arrived in physics carrying a message that nobody expected and nobody was prepared for. It told physicists that the universe possesses hidden properties of matter, properties that are completely invisible under ordinary circumstances, but become impossible to ignore at high energies. Its paradoxical behavior, created in an instant but lingering for what felt like forever, was not a glitch or an anomaly or an experimental artifact. It was a signal. The strong force recognized strangeness and obeyed it absolutely. The weak force recognized strangeness and casually ignored it. This asymmetry between forces, this selective obedience to a hidden quantum number, was the first major indication that the forces of nature relate to each other in deep, subtle, and non-obvious ways. It was the first serious crack in the assumption that the subatomic world was simple and fully understood. And the Kaon was only getting started. Its most radical and most revolutionary surprises, the ones that would challenge physicists' most cherished beliefs about the fundamental symmetries of nature itself, was still waiting to be discovered. By the early 1960s, kaons had established themselves as the most important strange particles in physics. They had revealed a hidden property of matter called strangeness. They had demonstrated that the strong force and the weak force obeyed different conservation laws. They had turned the comfortable simplicity of the post-war particle world into a sprawling zoo of hundreds of newly discovered particles. But one enormous question remained unanswered. What actually is a kaon? Not what does it do, not how does it behave, but what is it made of? What is inside this thing? For nearly 2 decades after their discovery, nobody knew. Kaons were treated as fundamental objects, indivisible units of matter with specific masses, charges, spins, and strangeness values, but no known internal structure. You could measure a kaon's properties with extraordinary precision. You could predict how it would be produced and how it would decay. But if someone asked you what it was actually made of, what physical stuff sat inside this particle, giving it its mass and its strangeness, you had no answer. The question was considered almost meaningless. Particles were particles. They were the most basic things. You didn't ask what an electron was made of, because the electron was the bottom level. There was nothing further down. Many physicists assumed the same was true for mesons and baryons. They were fundamental. They had no parts. That assumption was spectacularly wrong. The first hints that something deeper lay underneath came not from looking inside particles directly, but from looking at how they were organized. By the late 1950s, the particle zoo had grown to unmanageable proportions. Hundreds of supposedly fundamental particles had been identified, each with its own mass, charge, spin, and strangeness value. If all these particles were truly fundamental, if they were all irreducible building blocks with no internal structure, then nature was absurdly complicated. There was no pattern, no rhyme, no reason, just a chaotic proliferation of objects that nobody could make sense of. But Murray Gell-Mann saw a pattern. In 1961, he proposed a classification scheme he called the Eightfold Way, borrowing the name from Buddhism's Noble Eightfold Path. The idea was mathematical. Gell-Mann showed that if you organize the known hadrons, the particles that feel the strong force, including protons, neutrons, pions, kaons, and all the heavier baryons and mesons, according to their electric charge and strangeness, they fell into geometric patterns. Specifically, they arranged themselves into neat multiplets, groups of particles fitting into the representations of a mathematical symmetry group called SU3. Think of it this way. Imagine you have a drawer full of buttons of all different sizes and colors. They seem random, but then you start sorting them and discover that every single button falls into one of a few specific categories. The large red ones always come with a particular number of holes. The medium blue ones always have a specific thickness. The small green ones always have the same diameter. What looked like chaos turns out to be highly organized. The buttons are not random at all, they are built according to a pattern, and once you see the pattern, you can predict what kinds of buttons should exist, even if you haven't found them yet. Gell-Mann did exactly this with particles. Mesons organized into octets, groups of 8 particles with related properties arranged in a hexagonal pattern when plotted by charge and strangeness. Baryons did the same, and when Gell-Mann arranged the heaviest known baryons into their SU3 pattern, he found a gap. 9 of the 10 positions in a particular grouping called a decouplet were filled by known particles, but one position was empty. The missing position called for a particle with electric charge -1, strangeness -3, and a specific predicted mass of roughly 1,680 million electron volts. No such particle had ever been observed. Gell-Mann predicted it must exist and gave it a name, the omega-. In 1964, experimenters at Brookhaven National Laboratory found it, with exactly the predicted charge, strangeness, and mass. The discovery was stunning. Gell-Mann had not just organized the particle zoo, he had used the organization to predict a particle nobody had seen before, and the prediction was confirmed. The Eightfold Way was not merely a filing system. It was telling physicists something deep and true about how particles are constructed. But what was the underlying reason for these patterns? Why did particles fall into octets and decouplets? What physical structure could produce such clean mathematical symmetry? The answer came in 1964, from 2 physicists working independently. Murray Gell-Mann, the same person who had proposed strangeness and the Eightfold Way, and George Zweig, a young physicist at CERN, both arrived at the same radical proposal. Hadrons are not fundamental. They have internal structure. Every hadron, every meson, and every baryon is built from smaller, more basic particles. Gell-Mann called them quarks, a word he borrowed from a passage in James Joyce's novel Finnegan's Wake. Zweig called them aces. The physics community adopted Gell-Mann's term. The original quark model proposed 3 types of quarks, called flavors. There was the up quark, carrying an electric charge of +2/3. There was the down quark, carrying an electric charge of -1/3. And there was the strange quark, also carrying an electric charge of -1/3, but distinguished from the down quark by one crucial property. It carried strangeness. Specifically, the strange quark had a strangeness value of -1. Every quark had a corresponding antiquark with opposite charge and opposite strangeness. The anti-up quark had charge -2/3. The anti-down quark had charge +1/3. The anti-strange quark had charge +1/3 and strangeness +1. The rules for building hadrons were elegantly simple. A baryon is made of 3 quarks. A meson is made of one quark and one antiquark. That's it. Those two rules, combined with three flavors of quarks, explain every single hadron that had ever been observed. Every entry in the particle zoo, every baryon and every meson was simply a different combination of up, down, and strange quarks and their antiquarks. The hundreds of supposedly fundamental particles were not fundamental at all. They were composite objects, built from just three types of building blocks. And now, finally, we can answer the question at the heart of this story. What is a kaon? A kaon is a meson. It is made of one quark and one antiquark, bound together by the strong force. What makes a kaon different from an ordinary pion or any other common meson is that one of its two constituent quarks is always a strange quark or a strange antiquark. That is what gives the kaon its strangeness. Strangeness is not some abstract quantum number floating around the particle like a label. It is a physical property carried by a physical object, the strange quark sitting inside the kaon. There are four types of kaons, and each one is built from a specific pair of quarks. The K+ is made of an up quark and an anti-strange quark. The up quark contributes an electric charge of +2/3. The anti-strange quark contributes an electric charge of +1/3 and a strangeness of +1. Add them together, and you get a particle with total charge +1 and strangeness +1. That is the K+, with the mass we already established, just under 500 million electron volts. The K- is the antimatter partner of the K+. It is made of a strange quark and an anti-up quark. The strange quark contributes charge -1/3 and strangeness -1. The anti-up quark contributes charge -2/3. Total charge is -1. Total strangeness is -1. Same mass as the K+, because matter and antimatter particles have the same mass. This symmetry between the K+ and K- is a direct consequence of a deep principle in physics called CPT symmetry, which states that swapping particles with antiparticles, reflecting space, and reversing time all at once leaves the laws of physics unchanged. The K0 is electrically neutral. It is made of a down quark and an anti-strange quark. The down quark contributes charge -1/3. The anti-strange quark contributes charge +1/3. These cancel exactly, giving 0 total charge. The anti-strange quark also contributes strangeness +1. The K0 is almost identical in mass to its charged cousins, just a few million electron volts heavier. The K0 bar is the antiparticle of the K0. It is made of a strange quark and an anti-down quark. The strange quark contributes charge -1/3 and strangeness -1. The anti-down quark contributes charge +1/3. Again, total charge is 0, but the strangeness is -1 instead of +1. The K0 and K0 bar have the same mass and the same electric charge, which is 0. The only thing that distinguishes them is their strangeness, which has opposite sign. This seemingly minor distinction will turn out to have monumental consequences for the history of physics, but that part of the story comes later. Now compare kaons to pions to see why the distinction matters. The most common pion, the pi+, is made of an up quark and an anti-down quark. No strange quarks involved, no strangeness at all. Its strangeness value is 0. The pi- is a down quark and an anti-up quark. Again, 0 strangeness. The pi0 is a quantum mechanical mixture of up and anti-up with down and anti-down. Still 0 strangeness. Pions are built entirely from up and down quarks and their antiquarks. They carry no strange quarks, and therefore they have no strangeness. They are the ordinary, everyday mesons of the subatomic world, the ones that Yukawa predicted as the carriers of the nuclear force. Kaons are the next step up. They are the lightest mesons that contain a strange quark or antiquark, and that single strange quark is what makes all the difference. It is what gives kaons their strange behavior, their slow decays, their paradoxical production patterns, and ultimately, their ability to reveal deep truths about the forces of nature. But why does having a strange quark make the kaon unstable? Why does it decay at all? The answer lies in the mass of the strange quark and the nature of the weak force. The strange quark is heavier than the up and down quarks, significantly heavier. The up quark has a mass of only about 2 million electron volts. The down quark has a mass of about 5 million electron volts. These are extraordinarily light. They are the two lightest quarks, the two most common, the two that make up virtually all the ordinary matter in the universe. Every proton and every neutron in your body is built from up and down quarks. The strange quark, by contrast, has a mass of about 95 million electron volts. That is roughly 20 times heavier than the down quark and nearly 50 times heavier than the up quark. It is a genuinely heavy particle by quark standards. And in the subatomic world, heavy particles are unstable. They want to decay into lighter particles, shedding their excess mass as energy, because nature always seeks the lowest energy state. A ball rolls downhill. A hot object cools. A heavy particle decays into lighter ones. This is not a choice. It is the relentless pull of thermodynamics and quantum mechanics working together. Any particle that can decay into lighter particles will eventually do so, unless some conservation law forbids it. The proton, for instance, is stable because it is the lightest baryon. There is no lighter combination of 3 quarks it could decay into without violating conservation of baryon number. The electron is stable because it is the lightest charged lepton. There is nothing lighter it could become. But the strange quark is not the lightest quark. It can transform into a lighter quark, shedding the mass difference as energy. And that transformation is what drives kaon decay. Here is exactly how it works. The strange quark inside a kaon can transform into an up quark or a down quark by emitting a W boson, one of the carrier particles of the weak force. The W boson is the agent of quark flavor change. It is the only particle in the Standard Model capable of changing one type of quark into another. The strong force cannot do this. The electromagnetic force cannot do this. Only the weak force, mediated by the W boson, can reach into a hadron and swap one quark flavor for another. Consider the decay of a K+. Inside the K+, you have an up quark and an anti-strange quark. The anti-strange quark emits a W+ boson and transforms into an anti-up quark. Now you have an up quark and an anti-up quark, which can annihilate each other, releasing their energy into the W+ boson and whatever it produces. The W+ boson itself is extremely heavy, about 80 billion electron volts, far heavier than the kaon, so it cannot actually appear as a real physical particle. Instead, it exists for only a fleeting instant as what physicists call a virtual particle, a quantum fluctuation that borrows energy from the vacuum for an incredibly brief period, just long enough to mediate the interaction before vanishing. The W+ then decays into lighter particles, perhaps a positron and a neutrino, or a pair of pions. The result is that the kaon disappears and lighter, more stable particles appear in its place. The total energy is conserved. The total charge is conserved. But strangeness is not conserved. It has changed from +1 to 0. The weak force has violated strangeness conservation, exactly as the Gell-Mann-Nishijima scheme predicted. And this is why Kaon decays are slow. The weak force is intrinsically feeble. The W boson is extremely massive, and the probability of producing even a virtual W boson in a low-energy process like Kaon decay is very small. The mathematics of quantum field theory relates the probability of a process to the mass of the mediating particle. The heavier the mediator, the less likely the process. The W boson is about 160 times heavier than the kaon itself. This enormous mismatch suppresses the decay rate dramatically. The kaon has to wait for a rare quantum fluctuation, a moment when the energy bookkeeping of the universe temporarily permits a virtual W boson to flicker into existence and carry out the transformation. That flickering is improbable, so the kaon waits and waits. By subatomic standards, it waits an eternity, about 10 to the -8 seconds for the charged kaons, which is 1,000,000 billion times longer than a strong interaction would take. This is the complete answer to the paradox that baffled physicists in the 1950s. The kaon is produced quickly because the strong force creates quark-antiquark pairs with no net change in strangeness. The kaon decays slowly because the only way to eliminate its strange quark is through the weak force, which requires a virtual W boson so heavy that the process is drastically suppressed. Fast birth, slow death. It is not a paradox at all once you see the quarks inside. It is the inevitable consequence of a heavy quark trapped inside a light particle, waiting for the feeble weak force to set it free. The quark model also explains why kaons are different from the heavier strange baryons like the lambda and sigma particles that were discovered alongside them. A lambda baryon, for example, is made of an up quark, a down quark, and a strange quark. 3 quarks instead of 2. That makes it a baryon, not a meson. It is heavier than a kaon, with a mass of about 1,116 million electron volts, more than twice the kaon mass. The lambda also carries strangeness -1, contributed by its strange quark. It decays through the weak force for the same reason the kaon does. Its strange quark must transform into a lighter quark via a virtual W boson, and that process is slow. But the lambda decays into different products, typically a proton and a pi-, because it contains 3 quarks and must produce a baryon in its final state. Conservation of baryon number demands it. The lambda cannot decay into pions alone because pions are mesons and carry no baryon number. Kaons, being mesons, have baryon number 0. They can decay entirely into pions, or into leptons like electrons and neutrinos, or into combinations of both. Their decay products are constrained only by the conservation laws that the weak force respects, namely conservation of charge, conservation of lepton number, and conservation of baryon number. Strangeness conservation is the one rule the weak force is allowed to break, and it does so every single time a kaon decays. This distinction between mesons and baryons, between 2 quark and 3 quark combinations, is fundamental. It determines what a particle can decay into, how long it lives, and what role it plays in the structure of matter. Baryons are the heavy, stable or semi-stable particles that make up atomic nuclei. Mesons are the lighter, always unstable particles that mediate forces between baryons and play starring roles in the study of fundamental symmetries. Kaons, as the lightest strange mesons, sit at the intersection of these two worlds. They are light enough to be produced easily, stable enough to travel measurable distances before decaying, and strange enough to carry information about the deepest workings of the weak force. The The quark model was not immediately accepted. When Gell-Mann and Zweig proposed it in 1964, many physicists were skeptical. The idea that protons, neutrons, and all the other hadrons were made of smaller particles was radical enough. But there were specific objections that made the proposal seem almost impossible. The most serious objection concerned the delta++ baryon. This particle has an electric charge of +2 and a spin of 3/2. In the quark model, it is made of 3 up quarks. But the Pauli exclusion principle, one of the bedrock rules of quantum mechanics, says that no two identical fermions can occupy the same quantum state. Quarks are fermions. 3 up quarks in the same spatial state with the same spin alignment should be forbidden. The delta++ seemed to violate a fundamental law of physics. The resolution came in 1965, when the concept of color charge was introduced. Each quark, in addition to its flavor, carries one of 3 color charges, whimsically named red, green, and blue. These have nothing to do with actual color. The names are just labels, but the crucial point is that the 3 up quarks inside the delta++ are not actually identical. One is red, one is green, one is blue. They differ in color charge, and therefore the Pauli exclusion principle is satisfied. Color charge would eventually become the foundation of quantum chromodynamics, the modern theory of the strong force. But that development, while essential for a complete understanding of quarks and hadrons, is a story that extends well beyond the Kaon. Another reason for skepticism was that nobody had ever seen an isolated quark. No experiment had ever produced a quark on its own, free and unbound. If quarks were real, why couldn't you knock one out of a proton and study it in isolation? The answer, which took years to work out fully, is a property called confinement. The strong force between quarks does not weaken with distance the way gravity or electromagnetism does. Instead, it stays constant or even increases as quarks are pulled apart. If you try to pull a quark out of a proton, the energy stored in the stretching strong force field eventually becomes large enough to create a new quark-antiquark pair from pure energy. The new antiquark binds to the quark you were pulling, forming a meson, and the new quark fills the gap in the proton. You never get an isolated quark, you always get new hadrons instead. It is as if quarks are connected by unbreakable elastic bands. The harder you pull, the more energy you put in, and eventually the band doesn't snap. Instead, a new band with a new quark at the end materializes from the energy, and you end up with 2 bound systems instead of 1 free quark. This is why no free quark has ever been observed. Quarks are permanently confined inside hadrons. You can study them indirectly by smashing hadrons together at high energy and observing the debris. You can infer their properties from the patterns of that debris, but you can never hold a quark in your hand. It is one of the strangest features of the strong force and one of the most important facts about the subatomic world. Despite the initial skepticism, evidence for quarks accumulated relentlessly. In the late 1960s and early 1970s, experiments at the Stanford Linear Accelerator Center fired high-energy electrons at protons and observed that the electrons scattered as if they were bouncing off small, hard, point-like objects inside the proton. This was eerily reminiscent of Rutherford's gold foil experiment from 1911, where alpha particles bouncing off concentrated nuclei revealed that atoms had small, dense cores. History was repeating itself one level deeper. Just as atoms turned out to contain nuclei, protons turned out to contain quarks. The scattering experiments matched the quark model's predictions in extraordinary detail. The number of hard scatterers, their charges, their spins, everything aligned. By the mid-1970s, quarks were accepted as real physical objects, not mathematical fictions. And with that acceptance, the kaon's identity was finally and fully resolved. A kaon is not a featureless blob of subatomic matter. It is not an irreducible building block. It is a structured object. Inside every kaon, two quarks are bound together by the constant exchange of gluons, the carrier particles of the strong force. One of those quarks is always a strange quark or a strange antiquark. The other is always an up quark, an anti-up quark, a down quark, or an anti-down quark. The strong force holds them together, gluons flying back and forth between the two quarks thousands of trillions of times per second, maintaining the bond. And the strange quark, sitting there inside the kaon, heavier than its partner, carrying its single unit of strangeness, is a ticking clock. It wants to transform. It wants to shed its excess mass and become a lighter quark. But the only force that can make that change happen is the weak force, which acts through the heavy, improbable virtual W boson. So the strange quark waits, trapped inside the kaon, bound by the strong force, until the weak force finally intervenes and allows it to decay. That is what a kaon is. A tiny prison for a strange quark, a composite particle built from the simplest possible combination of quarks that can carry strangeness, one quark and one antiquark, held together by the most powerful force in nature, but doomed to disintegrate by the feeblest one. It is a particle defined by the tension between opposing forces, created by the strong force, maintained by the strong force, and ultimately destroyed by the weak force. It exists in a no-man's land between stability and oblivion, living too long for the strong force to explain and dying too quickly for the weak force to seem irrelevant. And it was precisely this tension, precisely this delicate balance between the strong and weak forces, between creation and destruction, between the visible and the hidden, that made kaons the most valuable experimental tools in the history of particle physics. Because when physicists began studying kaon decays with the precision that accelerator experiments allowed, they found something even more shocking than strangeness itself. They found that the laws of physics, the most fundamental symmetries that everyone believed governed the universe, were not as perfect as they had assumed. The kaon was about to crack the mirror of nature itself. Physicists love symmetry, not in the everyday sense of something looking balanced or pretty, but in a much deeper, more precise sense. In physics, a symmetry is a transformation you can perform on the laws of nature that leaves those laws completely unchanged. It is a statement about invariance, about what stays the same when you change your perspective. And throughout the first half of the 20th century, several symmetries were considered sacred, so fundamental and so obvious that no serious physicist questioned them. One of the most intuitive was parity symmetry. Parity, often shortened to simply P, is the symmetry of mirror reflection. Imagine you are watching a physical process unfold. Now imagine watching the same process reflected in a mirror. Parity symmetry says that the reflected version should obey exactly the same laws of physics as the original. If something is possible in the real world, its mirror image should also be possible. If a particle spins clockwise and emits another particle to the left, the mirror image, a particle spinning counterclockwise and emitting to the right, should be equally valid. The laws of physics should not be able to tell the difference between a real event and its reflection. This is not just an abstract mathematical requirement, it has practical consequences. If parity is conserved, then certain processes are forbidden because they would look different in a mirror. If parity is violated, then nature itself is handed. It distinguishes between left and right at the most fundamental level. That would mean the laws of physics contain an intrinsic sense of direction, something that seemed philosophically abhorrent to most physicists. After all, why should the universe care about the difference between left and right? Left and right are human conventions. They depend on where you're standing and which way you're facing. Surely the fundamental laws governing the behavior of particles and forces should be indifferent to such arbitrary choices. And for decades, every experiment confirmed this expectation. The strong nuclear force conserves parity. The electromagnetic force conserves parity. Every interaction that physicists studied in the first half of the 20th century respected this mirror symmetry flawlessly. Parity conservation seemed like a bedrock truth, as reliable as conservation of energy or conservation of electric charge.
Nobody questioned it because nobody had any reason to question it. Then the Kaon created a problem. In the early 1950s, physicists studying Kaon decays noticed something deeply unsettling. There appeared to be two different types of kaons that were identical in mass, identical in charge, identical in strangeness, identical in spin, and identical in every measurable property. Yet they decayed in different ways. One type, called the theta meson, decayed into 2 pions. The other type, called the tau meson, decayed into 3 pions. This was the famous theta-tau puzzle, and it drove the physics community into agonized debate. Here is why it mattered. 2 pions and 3 pions have different parity. Parity is a multiplicative quantum number. Each pion has a specific intrinsic parity, which is negative. When you combine 2 pions, their total parity is negative times negative, which equals positive. When you combine 3 pions, their total parity is negative times negative times negative, which equals negative. So the 2 pion final state has positive parity, and the 3 pion final state has negative parity. If parity is conserved in the decay, the decaying particle must have the same parity as its decay products. A particle with positive parity can decay into 2 pions, but not 3. A particle with negative parity can decay into 3 pions, but not 2. The theta and tau mesons could not be the same particle if parity were conserved. One decayed into a positive parity final state, the other into a negative parity final state. They must be 2 different particles, each with its own parity. But every other property of the theta and tau was exactly the same. Their masses matched to extraordinary precision. Their charges matched. Their strangeness values matched. Their spins matched. The odds of 2 fundamentally different particles sharing every single observable property except their decay modes seemed absurdly unlikely. It was as if you found 2 people with the same height, weight, eye color, fingerprints and DNA, but one of them was left-handed and the other right-handed, and you insisted they must be 2 entirely different human beings. The physics community was stuck. Either the theta and tau were different particles with an almost miraculous coincidence of properties, or they were the same particle and parity was not conserved in the weak interaction responsible for their decay. Neither option was comfortable. The first required accepting an extraordinary coincidence with no explanation. The second required abandoning a symmetry that had been trusted for decades. In 1956, 2 young Chinese-American theoretical physicists, Sungdao Li and Chen-Ning Yang, examined the situation with fresh eyes. They conducted a careful, systematic review of all existing experimental evidence for parity conservation. What they found was startling. While there was overwhelming evidence that the strong force and the electromagnetic force conserve parity, there was essentially no experimental evidence one way or the other for the weak force. Nobody had ever actually tested whether the weak force respects parity. Everyone had simply assumed it did, because the other forces did, and because it seemed philosophically natural. Li and Yang had uncovered an enormous blind spot in experimental physics. One of the most fundamental symmetries in nature had never been tested in the very domain where it might fail. Li and Yang did more than identify the gap. They proposed specific experiments that could settle the question. If the weak force violates parity, they argued, certain measurable asymmetries should appear in weak decays. Specifically, if you take a sample of radioactive nuclei, align their spins in the same direction using a powerful magnetic field, and watch which direction the decay electrons are emitted, parity conservation predicts the electrons should come out equally in both directions, toward the north pole and the south pole of the aligned nuclei. A mirror reflection would reverse the nuclear spin, but not the electron emission direction. If the electrons come out symmetrically, the process looks the same in a mirror and parity is conserved. If the electrons preferentially emerge in one direction, the process looks different in a mirror and parity is violated. Chien-Shiung Wu, an experimental physicist at Columbia University, widely regarded as one of the most meticulous and brilliant experimenters of her generation, took up the challenge. The experiment was extraordinarily difficult. It required cooling cobalt-60 nuclei to temperatures just a fraction of a degree above absolute zero, about 1/100th of a degree, cold enough that thermal vibrations didn't randomize the nuclear spins. A powerful magnetic field aligned the spins of the cobalt-60 nuclei so they all pointed the same direction. Then Wu and her collaborators, working with a team at the National Bureau of Standards in Washington, measured the direction in which electrons were emitted as the cobalt-60 underwent beta decay, a process governed entirely by the weak force. The result was unambiguous and devastating. The electrons did not come out equally in both directions. They came out preferentially opposite to the direction of the nuclear spin. The asymmetry was large and unmistakable. Parity was violated. Not by a small amount, not subtly, blatantly. The weak force does not respect mirror symmetry. Nature, at the most fundamental level, distinguishes between left and right. The universe is handed. The announcement of Wu's result in January of 1957 sent shockwaves through the physics community. Physicists had been so confident in parity conservation that many simply could not believe the result at first. Wolfgang Pauli, one of the great theoretical physicists of the 20th century, and a man famous for his sharp and often caustic skepticism, had written in a letter just weeks before the result was announced that he was willing to bet a large sum that the experiment would confirm parity conservation. He lost the bet. When he heard the result, he reportedly said that he could not believe God was a weak left-hander. But the experiment was airtight. Other groups quickly reproduced it using different nuclei and different techniques. Parity violation in the weak force was real. After Pauli's reaction and the confirmation of parity violation, the script moves quickly to the Nobel Prize, and then to the CP symmetry rescue. What is missing in that transition is a concrete physical picture of what parity violation actually looks like at the particle level. The script tells the audience that nature distinguishes between left and right, and that the universe is handed. But it never shows them what that handedness physically means for particles. Specifically, the discovery revealed that neutrinos produced in weak decays are always left-handed, spinning one way relative to their direction of motion, never the other. No right-handed neutrino has ever been observed. This is the single most vivid and striking manifestation of parity violation, and stating it concretely before introducing CP symmetry would make the CP rescue feel more logical and more earned, because the script already references left-handed neutrinos when explaining CP symmetry, but the audience has not yet been told where that fact comes from. Li and Yang were awarded the Nobel Prize in Physics in 1957, the same year the experiment was published. The speed of the recognition reflected the magnitude of the discovery. A symmetry everyone had taken for granted had been shown to be false. And the particle that had first hinted at this failure, the particle whose mysterious theta-tau puzzle had provoked the entire investigation, was the Kaon. The theta and tau mesons were indeed the same particle. They were both kaons. The kaon decayed into 2 pions sometimes, and 3 pions other times, because the weak force does not conserve parity. There was no paradox. There was no coincidence. There was only a broken symmetry that nobody had thought to test. But physicists are resourceful. When one symmetry falls, they reach for a deeper one. and in the aftermath of parity's collapse, the physics community quickly rallied around a new candidate. The idea was this: parity violation means the laws of physics change when you reflect them in a mirror. But maybe that's not the whole story. Maybe if you perform two operations simultaneously, reflecting in a mirror and swapping every particle with its antiparticle, the laws of physics stay the same. Swapping particles with antiparticles is called charge conjugation, denoted C. Combining charge conjugation with parity gives you a combined symmetry called CP. CP symmetry is a more subtle and more powerful claim than parity alone. It says that the mirror image of a process involving matter should look exactly the same as the original process involving antimatter. If a neutrino is always left-handed, which parity violation showed to be true, CP symmetry says that an antineutrino should always be right-handed. The violation in one domain is exactly compensated by an opposite violation in the other domain. Individually, C and P are broken, but together, CP might still hold. And for a few years, this seemed to work perfectly. Every experiment that had revealed parity violation was also consistent with CP symmetry. The asymmetries in beta decay could be completely explained by the combined CP transformation. Physicists breathed a sigh of relief. Yes, the mirror was cracked, but a deeper, more elegant mirror had been found. Nature might not look the same in a mirror, but it would look the same in a mirror made of antimatter. The universe wasn't truly asymmetric after all. It just required a more sophisticated notion of symmetry. To understand what happened next, you need to understand something remarkable about neutral kaons. The K0 and K0 bar are distinct particles with opposite strangeness. The K0 has strangeness +1. The K0 bar has strangeness -1. They are different. But because they are both electrically neutral and can both decay into the same products, like pairs of pions, quantum mechanics allows something extraordinary to happen. They can mix. Mixing is one of the strangest and most beautiful phenomena in quantum mechanics. It means that a particle created as a pure K0 does not stay a pure K0. Over time, it evolves into a superposition, a quantum mixture of K0 and K0 bar, and then back again. The particle oscillates between being matter and antimatter, flickering between two identities like a coin spinning in the air, neither fully heads nor fully tails until it is observed. This oscillation is mediated by the weak force, which can change a K0 into a K0 bar through a process involving virtual quarks and W bosons. The two states talk to each other through quantum mechanical tunneling, constantly exchanging identity. This oscillation is not a metaphor. It is a physical, measurable process. If you could somehow tag a neutral kaon at the instant of its creation and confirm that it was born as a K0 with strangeness +1, and then check its identity a fraction of a second later, you would find that it has a measurable probability of having become a K0 bar with strangeness -1. Wait a little longer and it might have flickered back to a K0 again. The particle's identity is not fixed. It evolves with time, swinging back and forth between two quantum states that differ in a fundamental quantum number. Nothing else in everyday experience works this way. A hydrogen atom does not spontaneously become an antihydrogen atom. A proton does not oscillate into an antiproton. But a neutral kaon does exactly this, and it does it continuously throughout its brief existence. The oscillation was eventually measured directly. Physicists produced beams of neutral kaons with known strangeness at the moment of creation, and then allowed them to interact with matter further downstream. A K0 interacting with ordinary matter produces certain characteristic reactions. A K0 bar interacting with the same matter produces different reactions because its strange quark can combine with the protons and neutrons in the target in ways that the anti-strange quark of a K0 cannot. By measuring which type of reaction occurred at different distances from the production point, and therefore at different times after creation, physicists could map out the oscillation directly. They could watch the probability of being a K0 rise and fall as the beam travelled, replaced periodically by the probability of being a K0 bar. The pattern matched quantum mechanical predictions with beautiful precision. This was the first system in all of physics where matter-antimatter oscillation was observed directly. It was a phenomenon so strange and so fundamentally quantum mechanical that nothing in classical physics even hinted it was possible. Because of this mixing, the K0 and K0 bar are not the most useful way to describe neutral kaons. Instead, physicists describe them in terms of two different combinations, two new states that are mixtures of K0 and K0 bar. If CP symmetry holds, these combinations are particularly clean. One combination, called K short, is the CP even state, a symmetric superposition of K0 and K0 bar. The other, called K long, is the CP odd state, an antisymmetric superposition. These two states have definite CP quantum numbers if CP symmetry is exact. And here is the crucial point. The CP quantum number determines what each state can decay into, just as parity determined what the theta and tau mesons could decay into. 2 pions have a CP value of +1. 3 pions have a CP value of -1. If CP symmetry is conserved, then K short, the CP even state, can decay into 2 pions. K long, the CP odd state, can only decay into 3 pions. This has a dramatic observable consequence. Decaying into 2 pions is energetically favourable. There is more energy available for each pion to carry away, and fewer particles means fewer ways the process can go wrong quantum mechanically. 2 pion decays happen quickly. K short, which decays into 2 pions, has a lifetime of about 9 × 10⁻11 seconds. That is fast. K long, which can only decay into 3 pions, has a much harder time. 3 pion decays are slower because there is less energy per particle and the quantum mechanical probability is lower. K long lives roughly 570 times longer than K short, with a lifetime of about 5 × 10⁻8 seconds. This is a huge difference. K short vanishes almost instantly. K long lingers for hundreds of times longer. The two states, even though they are made of the same quarks, live completely different lives because CP symmetry restricts what each one can decay into. This difference in lifetimes created a beautiful experimental opportunity, and it was this opportunity that led to one of the most important discoveries in the history of physics. In 1964, James Cronin and Val Fitch, working at Brookhaven National Laboratory, designed an experiment to study neutral kaon decays. Their setup was conceptually simple. They produced a beam of neutral kaons and let it travel down a long pipe. At the beginning of the pipe, the beam contained both K short and K long. But K short decays so quickly that within a short distance, essentially all the K short particles had decayed away. What remained further down the pipe was a beam of nearly pure K long. If CP symmetry is exact, K long cannot decay into 2 pions. It can only produce 3 pions. So any decay observed far enough down the pipe should produce 3 pions, never 2. Cronin and Fitch placed their detectors far enough downstream that K short had vanished entirely. They watched for decays and carefully measured the number and momenta of the particles produced. If CP symmetry held, every single decay they saw should produce 3 pions. The experimental apparatus was a marvel of careful engineering. The kaon beam was produced by slamming high-energy protons from the Brookhaven accelerator into a fixed target, generating a spray of particles that included neutral kaons. Magnets swept away all the charged particles, leaving only the neutral ones. The remaining beam travelled through a helium-filled decay region, roughly 17 meters long, giving the short-lived K-short component time to decay away completely. By the end of the pipe, the beam was essentially pure K-long. Past the pipe, 2 spectrometer arms flanked the beam, each containing spark chambers that could track the paths of charged particles produced by Kaon decays. When a K-long decayed, the charged pions it produced flew into these detectors, leaving trails of sparks that were photographed and later analyzed by hand and by early computer programs. Cronin and Fitch ran the experiment for months, accumulating tens of thousands of decay events. The vast majority produced 3 pions, exactly as CP symmetry predicted. The data tapes piled up. The analysis was tedious and painstaking. Every event had to be reconstructed from the spark chamber photographs, the particle momenta calculated from the curvature of their tracks in the magnetic field, the invariant mass of the decay products computed to confirm whether the event was consistent with a genuine K-long decay or some form of background contamination. The experimenters were not looking for a revolution. They expected to confirm CP symmetry with high precision and publish a solid, respectable measurement. They had no reason to expect what the data actually showed. But it didn't. Among the thousands of 3-pion decays they recorded, they found a tiny but unmistakable handful of 2-pion decays. About 2 out of every 1,000 K-long decays produced 2 pions instead of 3. K-long was doing something CP symmetry explicitly forbade. It was decaying into a state with the wrong CP quantum number. CP symmetry was violated. The effect was small, only about 0.2% of decays, but it was real. Cronin and Fitch checked and rechecked their results meticulously. They considered every possible systematic error, every alternative explanation, every way the signal might be fake. Could stray K-short particles have contaminated the beam? No. The geometry of the experiment ruled that out. Could some other particle have mimicked the 2-pion signal? No. The kinematics, the precise energies and angles of the detected particles, matched 2-pion K-long decay exactly. Could the detectors have malfunctioned? No. Extensive calibration confirmed their performance. The result was solid. CP symmetry was broken. Not by a lot, not dramatically, but broken nonetheless. And in physics, a symmetry is either exact or it is not. There is no middle ground. You cannot be slightly symmetrical any more than you can be slightly pregnant. Either the laws of physics are invariant under CP transformation, or they are not. Cronin and Fitch showed they are not. The discovery was deeply disturbing because CP violation is different from parity violation in a fundamental way. Parity violation says the weak force distinguishes between left and right.
That was surprising but conceptually tolerable. You could still maintain that the overall laws of physics were balanced. CP violation says something far more radical. It says the laws of physics distinguish between matter and antimatter. Not just in some superficial bookkeeping way, not just in terms of having opposite charges, but in their actual physical behavior. A process involving particles does not have the exact same probability as the mirror image process involving antiparticles. Matter and antimatter are not perfect reflections of each other. The universe has a preference. Think about what this means. If you built a laboratory entirely out of antimatter, in an antimatter solar system, populated by antimatter physicists who performed the same experiments that Cronin and Fitch performed, they would get slightly different results. The laws of physics operating in their antimatter laboratory would not be exactly the same as the laws operating in our matter laboratory. This is not a difference in initial conditions or composition, it is a difference in the fundamental rules. The equations governing how particles interact contain a tiny but real asymmetry between matter
and antimatter. Cronin and Fitch were awarded the Nobel Prize in Physics in 1980 for this discovery. The citation specifically noted the discovery of violations of fundamental symmetry principles in the decay of neutral K mesons. It took 16 years from the discovery to the prize, a relatively long delay that reflected how difficult the result was for the physics community to process. Many physicists initially hoped some loophole would be found, some way to restore CP symmetry. No loophole was found. The result has been confirmed and refined by dozens of subsequent experiments, each one measuring CP violation with greater precision. It is one of the most firmly established facts in particle physics. After the fall of CP symmetry, one final symmetry remained. CPT symmetry, the combination of charge conjugation, parity, and time reversal. CPT symmetry states that if you simultaneously swap every particle with its antiparticle, reflect everything in a mirror, and run time backward, the laws of physics remain unchanged. Unlike C, P, and CP individually, CPT symmetry is guaranteed by the most general mathematical structure of quantum field theory. Any quantum field theory that is consistent with special relativity and has a stable ground state must respect CPT symmetry. This is not just an empirical observation, it is a mathematical theorem proved by multiple physicists in the 1950s and 60s. CPT symmetry has an important consequence for CP violation. If CPT is exact but CP is violated, then T symmetry, time reversal symmetry, must also be violated. The three transformations are linked. If the combination is exact and one component is broken, another must be broken in a compensating way. The discovery of CP violation in kaons therefore implied that time reversal symmetry is also violated. The laws of physics run slightly differently forward and backward in time, at least where the weak force is concerned. This implication was eventually confirmed directly. In 1998 and in subsequent years, experiments at CERN and at Fermilab directly measured time reversal violation in the neutral kaon system, confirming that T symmetry is indeed broken in a manner consistent with CP violation and exact CPT symmetry. The universe not only distinguishes between left and right, and between matter and antimatter, it even distinguishes between the past and the future at the level of fundamental particle interactions. What made CP violation in kaons so significant was not just that it broke a symmetry, it was the kind of symmetry it broke. Parity violation had been shocking, but in some sense contained. It said the weak force tells left from right. That was strange, but it didn't obviously threaten any deep cosmological principle. CP violation was different. It reached further. It said that the fundamental equations governing particle interactions are not perfectly even-handed between matter and antimatter. It meant that somewhere inside the mathematical structure of the weak force, there was a built-in preference, a subtle tilt, an imbalance woven into the laws themselves. Physicists immediately recognized that this kind of asymmetry might have consequences far beyond the laboratory. If the universe began in a symmetric state, with equal amounts of matter and antimatter, and if the forces governing those particles treated the two differently, even by the smallest amount, then over time, that difference could accumulate. It could shape the evolution of the cosmos. It could determine what survived and what was annihilated. The implications were enormous, but working them out would require a theoretical framework that did not yet exist. Cronin and Fitch did not set out to reshape cosmology. They set out to study how neutral kaons decay. They were careful experimenters following the evidence, measuring what their detectors recorded and reporting what they found. But what they found turned out to carry implications that reached from the subatomic scale to the structure of the entire observable universe. The connection between a 2-part in 1,000 asymmetry in Kaon decays and the deepest questions about the origin of matter would become one of the most remarkable links in all of science. But understanding that link required new theoretical tools and new particles that nobody had yet imagined. The Kaon had already revealed hidden properties of matter through strangeness. It had already contributed to the particle zoo that demanded the quark model. And now it had shattered the symmetry between matter and antimatter, hinting that the consequences might reach far beyond particle physics. The full story of those consequences, the way CP violation reshaped the standard model and drove the prediction of entirely new quarks, was about to unfold. The discovery of CP violation in neutral kaons was not the end of a story. It was the beginning of one. And the story it began reaches from the smallest measurable distances in particle physics to the largest observable structures in the cosmos. From the behavior of individual quarks to the question of why the universe contains anything at all. To understand why CP violation mattered so profoundly beyond the laboratory, you need to travel back to 1967, 3 years after Cronin and Fitch's experiment, when a Soviet physicist named Andrei Sakharov published a short but extraordinary paper. Sakharov was already famous, not for particle physics, but for his role in developing the Soviet hydrogen bomb. He was one of the most brilliant physicists of the 20th century, and in 1967 he turned his attention to one of the deepest puzzles in cosmology. Why is the universe made of matter instead of antimatter? The question sounds simple, but it is devastating. The laws of physics, as they were understood at the time, seemed to treat matter and antimatter with perfect symmetry. Every reaction that could produce a particle could equally produce an antiparticle. The Big Bang, which created the universe roughly 13.8 billion years ago, should have produced exactly equal quantities of matter and antimatter. And when the universe cooled enough for particles and antiparticles to meet, they should have annihilated each other completely. The result should have been a universe filled with nothing but radiation. No protons, no neutrons, no atoms, no stars, no planets, no people. Just light. Yet here we are. The universe is overwhelmingly made of matter. Stars burn with matter. Galaxies are built from matter. You are made of matter. Antimatter, in bulk, is essentially absent from the observable cosmos. Something must have created a tiny surplus of matter over antimatter in the early universe, a surplus so small that for every billion antiparticles, there were approximately 1,000,000,001 particles. When the annihilation was complete, that one extra particle per billion survived, and those survivors are everything we see. Sakharov identified 3 conditions that any physical process must satisfy if it is to generate this matter-antimatter asymmetry from an initially symmetric starting point. First, there must exist interactions that violate baryon number conservation. Baryon number is the quantum number that counts the number of baryons, particles like protons and neutrons. If baryon number is always conserved, you can never create more matter than antimatter, because every baryon created would be accompanied by an antibaryon. Second, the universe must not be in thermal equilibrium during the period when the asymmetry is generated. In thermal equilibrium, every process and its reverse happen at equal rates, so any asymmetry created would be immediately erased. The universe must be out of equilibrium, expanding and cooling rapidly enough that the asymmetry is frozen in before it can be undone. Third, and this is where kaons enter the picture, the laws of physics must violate both C symmetry and CP symmetry. C violation alone is not enough. If the laws of physics violate C but preserve CP, then the rate at which matter is created from some process would differ from the rate of antimatter creation in the mirror image process. But the CP conjugate process would compensate, and the total rates would balance out. Only if CP itself is violated can the total production of matter exceed the total production of antimatter, or vice versa. CP violation is the ingredient that allows nature to prefer matter over antimatter at the level of fundamental law. Sakharov published his 3 conditions in 1967. At the time, only one example of CP violation was known in all of physics. The one Cronin and Fitch had discovered in neutral kaons 3 years earlier. That single observation, 2 pion decays appearing in a beam where CP symmetry said they should not, was the only experimental evidence that the third Sakharov condition could be satisfied. Without the kaon, there would have been no empirical basis for believing that CP violation existed at all. The entire theoretical framework for explaining why the universe contains matter would have had no experimental foundation. This connection between a laboratory measurement and a cosmic mystery is one of the most remarkable in all of science. A particle that lives for less than 100 millionth of a second, too small to see, too short-lived to touch, decaying inside a detector in a basement at Brookhaven National Laboratory, turned out to carry information about why stars and galaxies and human beings exist. The kaon's tiny imperfection, its failure to respect CP symmetry by 2 parts in 1,000, is linked to the existence of everything. Now, it is important to be precise here. The amount of CP violation observed in kaons is far too small to account for the full matter-antimatter asymmetry of the universe. Detailed calculations show that kaon CP violation by itself produces an asymmetry many orders of magnitude smaller than what is needed. There must be additional sources of CP violation beyond what kaons reveal. This is one of the great open problems in physics. The standard model, as currently formulated, does not contain enough CP violation to explain the observed matter-antimatter asymmetry. Something is missing. Some new physics, some new source of CP violation beyond the standard model must exist. But the kaon established the principle. It proved that CP violation is real, that nature does distinguish between matter and antimatter, and that Sakharov's third condition is satisfied.
Whatever additional sources of CP violation exist, the kaon showed that such violation is a feature of the physical world, and not merely a theoretical possibility. The discovery of CP violation in kaons also had profound consequences for the theoretical structure of particle physics. In the years following Cronin and Fitch's experiment, theorists scrambled to understand how CP violation could arise within the existing framework of particle physics. Where did it come from? What mechanism could produce an asymmetry between matter and antimatter in the weak interaction? The first critical step had already been taken in 1963, a year before CP violation was discovered, by an Italian physicist named Nicola Cabibbo. Cabibbo was studying how quarks transform into each other through the weak force. As we discussed earlier, the weak force is the only force that can change one flavor of quark into another. It does this through the emission or absorption of a W boson. But Cabibbo noticed something important. When a strange quark decays into an up quark by emitting a W- boson, the rate of this process is slower than you would expect if the weak force coupled to all quarks equally. The strange quark seemed to be partially reluctant to transform, as if the weak force's grip on it was weaker than its grip on the down quark. Cabibbo proposed that the weak force does not couple to quarks in a simple flavor-by-flavor way. Instead, the quark states that participate in weak interactions are not the same as the quark states that have definite masses. They are mixtures. The down quark that the weak force sees is actually a quantum mechanical mixture of the down quark and the strange quark that have definite masses. Cabibbo introduced a single parameter, called the Cabibbo angle, that quantified the degree of mixing. This angle, measured experimentally to be about 13 degrees, explained why strange quark decays were slower than down quark decays.
The weak force couples to a rotated version of the quark flavors, and the rotation angle determines the relative rates. This was an elegant idea, and it worked beautifully for two quark flavors. But in 1973, two Japanese physicists, Makoto Kobayashi and Toshihide Masukawa, realized something extraordinary. They asked a deceptively simple question. What is the minimum number of quark generations needed to produce CP violation within the standard framework of quantum field theory? At the time, only 3 quarks were known: up, down, and strange. These 3 quarks formed a partial pattern, suggesting they belonged to pairs or generations. The up and down quarks seemed to go together, forming the first generation. The strange quark seemed to be part of a second generation, but its partner, a quark with charge plus 2/3 and strangeness 0, had not yet been found. This hypothetical partner, the charm quark, had been predicted on theoretical grounds, but remained unobserved. Kobayashi and Masukawa extended Kabibo's mixing framework from 2 quark flavors to the general case. They showed that if you have only 2 generations of quarks, 4 quarks total, the mixing can be described by a single angle, Kabibo's angle, and 1 phase parameter. But the phase parameter can always be eliminated by redefining the quark fields. With only 2 generations, CP violation is mathematically impossible within this framework. No matter how you set the parameters, the theory remains CP symmetric. 2 generations are not enough. With 3 generations of quarks, 6 quarks total, the situation changes dramatically. The mixing is now described by a 3x3 matrix, the Kabibo-Kobayashi-Masukawa matrix, universally known as the CKM matrix. This matrix contains 3 mixing angles and 1 complex phase. And that complex phase cannot be eliminated. It is a genuine physical parameter that enters the theory in a way that makes CP violation not just possible, but natural. If the phase is non-zero, CP violation occurs automatically, built into the fundamental equations of the weak force. This was a staggering prediction. In 1973, when Kobayashi and Masukawa published their paper, only 3 quarks were known, and even the existence of the charm quark was not yet confirmed. Kobayashi and Masukawa were predicting the existence of an entire 3rd generation of quarks, 2 completely new quarks that nobody had ever observed, based on the requirement that the theory must be able to accommodate CP violation. They were saying that the small effect Cronin and Fitch had measured in Kaon decays demanded the existence of new fundamental particles. The predictions were confirmed with breathtaking precision over the following 2 decades. The charm quark, the partner of the strange quark in the 2nd generation, was discovered in 1974 at both Brookhaven National Laboratory and the Stanford Linear Accelerator Center simultaneously. 2 independent teams found a narrow resonance, a particle called the J-psi, which was a bound state of a charm quark and an anti-charm quark. The discovery was so striking and so clearly significant that both team leaders, Burton Richter and Samuel Ting, shared the Nobel Prize in 1976. The bottom quark, the first member of the 3rd generation, was discovered in 1977 at Fermilab by Leon Lederman and his collaborators. They found another narrow resonance called the upsilon, which was a bound state of a bottom quark and an anti-bottom quark. The bottom quark had a charge of -1/3, the same as the down and strange quarks, but it was far heavier, with a mass of about 4,200,000,000 electron volts. Its discovery confirmed that a 3rd generation existed. The top quark, the final member of the 3rd generation and the partner of the bottom quark, was not found until 1995, again at Fermilab. It turned out to be astonishingly heavy, with a mass of about 173 billion electron volts, nearly as heavy as an entire gold atom. It is by far the heaviest known fundamental particle. Its enormous mass made it extremely difficult to produce and detect, requiring the highest energy collisions available at the time. With all 6 quarks discovered, the CKM matrix could be fully measured. Decades of painstaking experiments measuring quark mixing rates, CP violating asymmetries, and rare decay processes pinned down the 3 mixing angles and the crucial complex phase with ever-increasing precision. The results were consistent and beautiful. The CKM matrix is unitary, meaning its mathematical structure is self-consistent. The complex phase is non-zero, meaning CP violation is built into the matrix exactly as Kobayashi and Muskawa predicted. Every measured CP violating effect in Kaon decays matched the predictions of the 3-generation framework. Kobayashi and Muskawa were awarded the Nobel Prize in Physics in 2008, 35 years after their original paper. The citation honored their discovery of the origin of the broken symmetry, which predicts the existence of at least 3 families of quarks in nature. Their work is one of the most remarkable examples in physics of pure theoretical reasoning, motivated by a single experimental observation, leading to the prediction of entirely new fundamental particles that were later confirmed to exist. And the experimental observation that started it all was CP violation in Kaon decays. The Kaon's influence did not end with the confirmation of the CKM matrix. Once the 3-generation framework was established, physicists realized they could use other particles, particularly B mesons, to study CP violation with greater precision.
B mesons contain bottom quarks, and because the bottom quark is much heavier than the strange quark, CP violating effects in B meson decays are much larger than in Kaon decays, reaching tens of percent rather than fractions of a percent. This made B mesons natural laboratories for precision tests. In the late 1990s and early 2000s, 2 enormous experiments were built specifically to study CP violation in B mesons. The Barbar experiment at the Stanford Linear Accelerator Center and the Bell experiment at the Keck Laboratory in Japan each produced hundreds of millions of B meson pairs and measured their decays with extraordinary precision. Both experiments confirmed CP violation in the B meson system, and both found results fully consistent with the CKM matrix predictions. The pattern was clear. CP violation is real. It arises from the complex phase in the CKM matrix, and it appears wherever the theory says it should. But here is what makes kaons still uniquely valuable even after all this progress. The CKM matrix explains CP violation within the standard model. It is a complete and consistent description of quark mixing and the resulting asymmetry between matter and antimatter. But as we discussed, the standard model's CP violation is not enough to explain the matter-antimatter asymmetry of the universe. There must be additional sources of CP violation from physics beyond the standard model. And kaons, precisely because their standard model CP violation effects are so small, are extraordinarily sensitive probes for detecting new contributions. Think of it this way. If you are looking for a faint signal, you want to measure in a place where the background is low. B meson CP violation is large, tens of percent. Any new physics contribution would have to be very large to stand out above that strong standard model signal. But Kaon CP violation is tiny, parts per thousand. A new physics contribution of even modest size would show up clearly against that quiet background. Kaons are like a dark, silent room where even a whisper can be heard. B mesons are like a noisy concert hall where only a shout would be noticed. The mechanism that makes this possible is the same quantum mechanical principle that governs kaon decay itself. Remember that a kaon decays because its strange quark emits a virtual W boson, a particle far too heavy to be produced for real at the energies involved, but one that can flicker into existence for an unimaginably brief instant thanks to the uncertainty principle. That virtual particle changes the strange quark into a lighter quark and then vanishes, leaving behind the decay products.
The key insight is that virtual particles do not need to be produced for real. They borrow energy from the vacuum, exist for a fleeting moment, influence the outcome of the process, and disappear. And this trick is not limited to W bosons. Any particle that exists in nature, whether we have discovered it yet or not, can appear as a virtual particle inside these quantum loops if the mathematics of the interaction allows it. A hypothetical heavy particle, something with a mass of tens of trillions of electron volts, far beyond the reach of any collider ever built or currently planned, could still pop into existence as a virtual particle during a rare Kaon decay. It would never be produced directly, you would never see it in a detector, but its brief virtual appearance would slightly alter the probability of that decay occurring. The rate would shift, perhaps by a few percent, perhaps less. And if your theoretical prediction for that rate is precise enough, and your experimental measurement is accurate enough, you would notice the discrepancy. The numbers would not match. Something unseen would be leaving its fingerprint on the data. This is why physicists sometimes call rare decay experiments indirect searches. They do not find new particles by creating them. They find them by detecting the faint shadows those particles cast on processes we can measure. This is why Kaon physics remains an active and vital field of research today, more than 70 years after kaons were first discovered. Several major experiments around the world are dedicated specifically to studying rare Kaon decays, searching for tiny deviations from standard model predictions that would signal the presence of new physics. One of the most important measurements being pursued is the rate of an extraordinarily rare decay of the K+ into a pi+ and a pair of neutrinos. In the standard model, this decay is predicted to occur roughly once in every 10 billion K+ decays. That is an absurdly rare process. If you produced 10 billion kaons, you would expect to see it happen roughly once. The reason it is so rare is that it proceeds through quantum loops involving virtual top quarks and W bosons, and the same CKM matrix elements that produce CP violation also suppress this decay to a tiny rate. Because the standard model prediction is so precise and so small, even a modest contribution from new physics would change the rate noticeably. Measuring this decay rate with sufficient precision to compare against the prediction is one of the holy grails of modern particle physics. The NA62 experiment at CERN is currently dedicated to this measurement. It produces intense beams of K+ mesons and watches for this ultra-rare decay with sophisticated detectors designed to reject the overwhelming backgrounds from more common decay modes. Every candidate event must be scrutinized with painstaking care, because for every genuine signal event, there are billions of background events that could mimic it. The experiment has already observed a handful of candidate events, and the measured rate is consistent with the standard model prediction so far. But the precision is still limited. More data, more running time, and improved techniques will gradually sharpen the measurement until it either confirms the standard model precisely or reveals a discrepancy pointing to new physics. A parallel effort targets the neutral Kaon equivalent, the decay of K long into a pi0 and a pair of neutrinos. This decay is even rarer, predicted to occur roughly once in every 30 billion K long decays, and it is directly sensitive to the imaginary part of specific CKM matrix elements, making it one of the cleanest possible measurements of CP violation in the quark sector. Any deviation from the predicted rate would be an almost unambiguous signal of new physics, because the theoretical prediction is so clean. Unlike many other processes in particle physics, this decay can be calculated with very small theoretical uncertainties. The standard model makes a sharp, precise prediction, and nature either matches it or does not. The Koto experiment at the J-Park facility in Japan is pursuing this measurement. It is an extraordinarily challenging experiment because the final state contains a pi-0, which decays almost immediately into 2 photons and a pair of neutrinos, which are invisible. The detector must identify events where a K-long enters. 2 photons come out with the right energy and angle, and nothing else is detected. The background rejection requirements are staggering. Every stray particle, every accidental coincidence, every detector malfunction could fake a signal. The experimenters must understand their detector and their backgrounds with almost superhuman precision. These experiments represent the cutting edge of fundamental physics. They are not discovering new particles in the dramatic sense of seeing something pop out of a collision. They are making precision measurements of exquisitely rare processes, comparing those measurements against equally precise theoretical calculations, and searching for the faintest possible hints that the standard model is incomplete.
It is a different kind of physics than the one that discovered quarks and W bosons. It is quieter, more patient, more meticulous. But it is no less important because the stakes are the same. Any deviation from the standard model in rare Kaon decays would point directly to new fundamental physics, potentially the same new physics responsible for the matter-antimatter asymmetry of the universe. There is something almost poetic about the Kaon's trajectory through the history of physics. It arrived uninvited, an accidental byproduct of cosmic ray collisions that nobody was looking for and nobody expected. It caused confusion. Its behavior made no sense under the rules that governed every other known particle. Physicists gave it the name strange, not out of affection, but out of frustration. It was the particle that refused to follow the script. But every time physicists tried to explain the Kaon's behavior, they were forced to discover something fundamentally new about the universe. The Kaon's slow decay revealed strangeness, a hidden quantum number that nobody had imagined. Strangeness led to the eightfold way, the classification scheme that organized the particle zoo into mathematical patterns. Those patterns led to the quark model, revealing that protons, neutrons, and hundreds of other supposedly fundamental particles were actually built from smaller building blocks. The Kaon's theta-tau puzzle provoked the discovery that the weak force violates parity, overturning a symmetry that had been trusted for decades. The neutral Kaon's CP violation shattered the deeper symmetry between matter and antimatter, pointing toward the explanation for why the universe contains anything at all. And CP violation demanded the existence of 3 generations of quarks, a prediction that was confirmed over the next 2 decades as charm, bottom, and top quarks were discovered one by one. No other single particle has driven so many fundamental discoveries. No other particle has been so consistently surprising, so reliably productive, so stubbornly important. The Kaon is not the heaviest particle, or the rarest, or the most exotic. It is a modest meson, a bound state of 1 quark and 1 antiquark, with a mass about half that of a proton and a lifetime measured in 100 millionths of a second. By the standards of the particle zoo, it is unremarkable, but its behavior has repeatedly exposed hidden truths about the fundamental structure of reality, truths that no amount of pure theoretical reasoning could have uncovered without the experimental surprises the Kaon provided. Today, the Kaon continues this tradition. It sits at the center of a global experimental program designed to push the standard model to its limits. If new physics exists at energy scales beyond the reach of current colliders, rare Kaon decays may be the first place it reveals itself. The Kaon's sensitivity to quantum effects from heavy, undiscovered particles makes it a telescope aimed not at the sky, but at the unknown laws of nature. What physicists find in the next generation of Kaon experiments could reshape particle physics as profoundly as the Kaon reshaped it in the 20th century. When you look at the history of this particle, one lesson emerges with overwhelming clarity. The universe is stranger and less symmetrical than physicists assumed. Every time they believed they understood the rules, every time they thought the symmetries were settled,
the Kaon proved them wrong. It revealed hidden properties where none were expected. It broke symmetries that seemed unbreakable. It demanded the existence of particles that nobody had imagined. It connected the microscopic behavior of subatomic matter to the cosmic question of why anything exists at all. And it did all of this not through dramatic explosions or spectacular displays of energy, but through the quiet, patient, meticulous accumulation of tiny deviations from expectation.
The Kaon is a reminder that nature does not owe us simplicity. The universe is not obligated to be elegant or symmetric or easy to understand. It is what it is, and our job as a species capable of asking questions about it is to follow the evidence wherever it leads, even when it leads to places we did not want to go, even when it shatters assumptions we had come to cherish. The Kaon taught physicists this lesson more forcefully than any other particle in history. It told them that the symmetries of the universe are imperfect, that matter and antimatter are not mirror images, that the laws of physics contain a built-in preference that makes the existence of the material world possible. And it told them all of this in the quietest possible voice, through a 2-part in 1,000 asymmetry in the decay of a particle that lives for less than 100 millionth of a second. That is what a kaon is. And that is why it changed particle physics forever.